October 1943. Inglewood, California. The relentless desert sun beat down on North American Aviation's hangars, the roar of Merlin engines a constant symphony of war. Sergeant John Farah, a mechanic from Detroit, wiped grease from his hands. He knew the P-51 Mustang was a marvel, destined to sweep the skies over Germany, but he also knew its deadly secret, a fatal flaw at altitude, a ghost in the machine that stiffened controls and stole precious seconds. Seconds that meant the difference between life and death, between returning home or falling in flames. And Farah, against every order, every engineering protocol, had a solution. A solution so simple, so audacious, that no one would ever officially approve it. This isn't a story of grand designs or cutting-edge technology. It's the untold account of a lone mechanic, a clandestine modification, and the desperate gamble that transformed America's deadliest fighter into an unstoppable legend. Before we dive in, let me know in the comments, where in the world are you watching this from today? To understand the daring secret that changed everything, we must journey back to 1943. The scent of aviation fuel mingled with the metallic tang of hot aluminum, a ubiquitous aroma in the North American Aviation plant in Inglewood, California. It was October 1943, and the relentless desert sun, even in its autumn descent, still baked the hangars, making the air shimmer above the runways. Inside, the roar of Rolls-Royce Merlin engines, undergoing their pre-flight run-ups, was a deafening, vibrating promise of power echoing through the cavernous spaces. These were the hearts of the P-51B Mustangs, sleek, silver arrows rolling off the assembly line at an astonishing rate, a testament to American industrial might. Each fighter was a meticulously crafted instrument of war, destined for the unforgiving skies over Europe, where the Luftwaffe waited. Amidst the organized chaos, Sergeant John Farah, 28 years old, and hailing from the gritty automotive lines of Detroit, moved with a quiet intensity. His olive-drab fatigues were permanently stained with grease, his hands calloused from years of working with wrenches and raw steel. Farah wasn't an engineer, not in the traditional sense. His formal education had ended after high school, before the war pulled him from a job at Chrysler and into the USAAF. But what he lacked in academic credentials, he more than made up for with an innate, almost tactile understanding of machines. He didn't just see components, he felt their purpose, heard their complaints, understood their intricate symphony. His current post was the final inspection line, the last barrier between a freshly built Mustang and its ferry flight to a combat theater. While other mechanics focused on their specific tasks, tightening a bolt, checking an electrical connection, Farah cultivated an obsessive habit. He devoured every defect report that crossed his desk, no matter how minor. He sought the patterns, the whispers of systemic failure hidden in routine paperwork. For weeks, a particularly insidious anomaly had been nagging at him, a consistent, unsettling complaint from the front lines and test pilots alike. The reports were damning. Controls stiffen, ailerons unresponsive, fighting the stick at altitude. These weren't isolated incidents. They came from Wright Field in Ohio, where rigorous flight tests pushed the Mustangs to their limits, and from the nascent operational units already flying them. The problem manifested above 20,000 feet, exactly where the savage aerial war over Germany was being waged. It was not merely an inconvenience, it was a death sentence waiting to happen. In the brutal ballet of a dogfight, where every fraction of a second counted, a pilot needing 8 seconds to roll his aircraft instead of 1, 2 seconds against a diving Messerschmitt Bf-109G6 was a pilot who wouldn't be coming home. The P-51B, equipped with the mighty Rolls-Royce Merlin engine, was meant to be revolutionary. Its predecessor, powered by the Allison V-1710, had been a superb low-altitude fighter but a plodding performer above 15,000 feet. Precisely where the Luftwaffe's formidable Bf-109s and Fw-190s reigned supreme, the Merlin's two-stage supercharger transformed the Mustang, granting it the power to reach 440 mph at 25,000 feet, allowing it to escort B-17s and B-24s all the way to Berlin and back. For the first time, American fighter pilots had a mount that could challenge the best German aircraft in their own domain. But this stiff controls issue threatened to negate that hard-won advantage. Intelligence reports on captured or downed Bf-109 G6s indicated that while the German fighter might be inferior in raw speed and range, its controls remained remarkably light and responsive even at extreme altitudes. The Germans had designed their control systems for high-altitude combat over Europe from the outset. The Mustang, initially conceived for low-level ground attack to British specifications, was being pushed into a role it was not entirely built for. The official explanations Farah overheard were always superficial. Pilot fatigue, cold weather effects, minor friction in the system. None of it made sense to him. The P-51's ailerons were aerodynamically balanced, its cable system conventional and robust. Why then did this problem specifically emerge at altitude, and so consistently? His visceral understanding screamed that something deeper was at play. Against the informal warnings of his immediate supervisor, Master Sergeant Frank De Palma, a gruff ex-merchant marine who ran the inspection line with a weary pragmatism, Farah began to dedicate his nights to the mystery. De Palma, a man who believed in following procedure to the letter, had initially dismissed Farah's obsession as chasing ghosts. He watched the younger man, lantern in hand, disappear into the belly of the aircraft long after his shift ended, a mixture of exasperation and grudging curiosity clouding his face. "Farah, you ain't an engineer," De Palma would grumble, though he never actively stopped him. "You got a job to do. Leave the brainwork to the guys with the fancy degrees." But Farah couldn't leave it. He needed to understand. Night after night, in the pale glow of a handheld lamp, he meticulously traced every control cable from the cockpit stick to the ailerons at the wingtips. He navigated the labyrinthine pathways through structural bulkheads, examining every pulley, every guide, every connection. He'd check cable tension, measure temperatures, and search for the slightest hint of abnormal friction or wear. His fingers, sensitive from years of manipulating intricate machinery, would run along the taut cables, feeling for any imperfection. The breakthrough came late one September night. A P-51B, serial number 43-434, had just returned from high-altitude flight testing at Edwards Air Force Base in the desert. It had been pushed hard, its systems stressed under the brutal extremes of scorching desert heat and the frigid thin air of 30 southern feet. As Farah crawled into the wing route, a place where the aileron cables passed through a series of guides, his lamp illuminated something subtle but profoundly significant. Using a magnifying glass, he found microscopic wear marks on the cable guides themselves, faint, almost invisible abrasions that shouldn't have been there on an aircraft with only 15 hours of flight time. These marks indicated lateral movement, a subtle vibration or misalignment within the guides, creating friction where none should exist. It was an epiphany that hit him with the force of an actual blow. The problem wasn't a defect in the cables or the ailerons. It wasn't a flaw in the basic design. It was far more insidious, a systemic failure born from the very environment the Mustang was designed to dominate. The P-51's aluminum airframe, like any metal structure, expanded and contracted with temperature changes. At sea level, bathed in the warmth of a California day, the fuselage held one specific geometry. But at 25, feet, where the outside air plunged to 40 degrees Celsius, while the cockpit and internal systems retained residual heat, different sections of the airframe were in different thermal states. Simultaneously, the immense aerodynamic loads encountered during high-G combat maneuvers, positive and negative, caused the fuselage to subtly twist and flex in ways the static design couldn't fully account for. Each of these microscopic flexions, each thermal variation, slightly altered the precise, meticulously engineered path the control cables traversed. Pulleys and guides, designed with precise tolerances for standard conditions, became microscopically misaligned. Each misalignment, no matter how small, created a new point of friction. Cumulatively, along dozens of feet of cables passing through multiple guides, these minute frictions added up. The result was the insidious tightening of the controls, precisely when the pilot most desperately needed precision and speed. transforming a potentially revolutionary fighter into a potential death trap. The ghost in the machine was not a malfunction. It was the machine itself, subtly changing shape under the crushing demands of high-altitude warfare. The revelation hit John Farrar with a clarity that banished the fatigue of sleepless nights. It wasn't a broken part. It was a breathing airframe, subtly twisting and contracting under the extremes of high-altitude flight. The engineers, with their slide rules and blueprints, designed for static conditions, for calculated tolerances. But the reality of combat at 25,000 feet, where the outside air temperature could plummet to 40 degrees Celsius, while the internal structure retained some residual warmth, created a dynamic, ever-shifting geometry. Every slight flex, every infinitesimal contraction or expansion, threw the precisely aligned pulleys and guides for the control cables just enough out of sync to create friction. Multiply that friction across dozens of feet of cable, through multiple passage points, and the sum was a heavy, unresponsive control stick, a death trap in a dogfight. Farrar sketched his solution on the back of a crumpled defect report, his grease-stained fingers moving with urgent purpose. It was so elegant, so deceptively simple it felt almost absurd. Instead of attempting a massive redesign of the entire control system, a process that would take months, if not years, of engineering analysis, structural testing, and bureaucratic approvals, potentially sidelining the P-51 at a critical juncture of the war. He would stabilize the cable paths. His idea involved using common, readily available materials. 12-gauge stainless steel safety wire, the kind used everywhere on an aircraft to secure bolts and turnbuckles. He envisioned small, precisely positioned tensioners, not to tighten the cables themselves, but to maintain the critical geometric alignment between the guides at specific stress points. There were 6 such critical points he identified where the aileron cables passed through longerons or structural bulkheads, areas prone to the most pronounced microflexing. These small wire loops, securely fastened, would act as subtle stabilizers, compensating for the airframe's thermal and aerodynamic contortions. The wire was strong enough to withstand combat vibrations and G-loads, yet flexible enough not to introduce new structural stresses. The cost? 18 cents per aircraft in materials. The installation time? Approximately 30 minutes. It was a mechanic's solution, born of pragmatism and an intuitive understanding of function over form, a fix that leveraged existing components and skills, bypassing the entire complex, time-consuming engineering pipeline. With his sketches and a detailed explanation, Farrar presented his idea to the supervisory engineers at North American Aviation in late October 1943. He stood before them, a grease-stained sergeant, facing men in crisp white shirts and ties, men with advanced degrees and years of design experience. He laid out his findings, the microscopic wear, the thermal expansion, the aerodynamic twist. He described how these cumulative microfrictions translated into the stiff controls that pilots were reporting. Then, with a quiet confidence, he presented his solution. The engineers listened, their expressions ranging from polite skepticism to outright incredulity. They acknowledged the reported problem. It was certainly on their radar. But Farrar's proposed fix, it was an affront to their established process, an elegant but non-scientific hack. Sergeant Farrar, one of the senior engineers, Dr. Arthur Jenkins, stated, his voice modulated but firm, "We appreciate your initiative. The problem of control forces at altitude is a known challenge. However, any modification to a critical flight control system must undergo rigorous engineering analysis, structural stress tests, and formal approval from the Army Air Forces. Your tensioners, as you call them, are based on anecdotal evidence, not empirical data. Introducing an unapproved foreign object into the control system could compromise structural integrity, create unforeseen resonance, or lead to entirely new failure modes. It is potentially dangerous." Another chimed in, "Sergeant, we understand your passion, but this isn't tinkering with a Ford assembly line. This is a P-51. We cannot risk the lives of our pilots on unverified field modifications, no matter how clever they seem. Your proposal is officially denied." Farrar felt a cold knot tighten in his stomach. They were right, of course, by the book. He was just a mechanic. But he knew he was right. He had felt the problem in his bones, traced its insidious path with his own hands. He had seen the wear marks, understood the physics. He wasn't guessing. He was observing and solving. To him, waiting for bureaucratic approval was tantamount to signing death warrants. He was instructed to return to his regular inspection duties and cease his notebook engineering. The injustice burned. Lives were on the line, American lives, battling the best the Luftwaffe had. Every P-51 that flew into combat with stiff controls was a Mustang fighting with one hand tied behind its back. He couldn't just stand by. Farah, fueled by a stubborn certainty and a profound sense of urgency, decided that if official channels wouldn't listen, he would create his own proof. The decision was not made lightly. What he was contemplating was insubordination, a direct violation of orders, and potentially, in wartime, an act of sabotage. It could lead to court-martial, prison, or worse. But the faces of the pilots in the defect reports, the descriptions of near misses and desperate maneuvers, haunted him. He pictured a Messerschmitt diving from the sun, the American pilot straining at a sluggish stick, unable to react quickly enough. The image was a powerful motivator. He needed help. Not formal, approved help, but quiet, trustworthy hands. Farah approached two mechanics he knew from the line, both young men like him, both with the same dedication to their craft and an unspoken frustration with the endless paperwork that seemed to bog down every decision. Private First Class Tommy Jenkins, a lanky kid from rural Georgia with a knack for precision, and Corporal Miguel "Mickey" Rodriguez, a strong, silent man from East LA with a meticulous eye for detail. Farah laid out his theory, showed them his crude diagrams, and explained the risks involved. "Look, I know what this looks like," Farah said, his voice low, almost a whisper against the constant hum of the plant. "But I've seen enough reports. This isn't just a minor issue. It's killing our guys. This fix. It's cheap, it's fast, and it works. I'm going to prove it." Jenkins swallowed hard, his eyes wide. Rodriguez simply nodded, a grim determination setting on his face. They were in. The biggest hurdle was Master Sergeant Frank De Palma. De Palma was a man of regulations, but he was also a man who had seen combat as a merchant marine, who understood the grim realities beyond the factory floor. He knew Farah was smart, even if he was a damn headache. Farah approached him cautiously, outlining his plan without explicitly asking for permission. He spoke of extra inspections, of fine-tuning, using euphemisms that De Palma clearly saw through. De Palma leaned against a workbench, a lit cigarette dangling from his lips, watching Farah. The younger man's passion was palpable, his conviction unwavering. De Palma knew the risks Farah was taking. He also knew the stories from the pilots. He took a long drag, exhaled a plume of smoke, and flicked the ash. "Farah," he said, his voice a low rumble, "you know the rules. I got a report to sign off on every plane that leaves my line, and my eyes. Sometimes they ain't what they used to be at night, especially when I got a stack of paperwork this high." He gestured vaguely towards a pile of forms. "I might just miss some things, understand?" It was tacit approval, a silent complicity that spoke volumes. De Palma wouldn't openly endorse it, but he wouldn't stop it either. He would conveniently not see the unauthorized work. It was all the support Farah needed. The target aircraft was P-51B, serial number 43-12434. The very Mustang that had returned from Edwards AFB with the telltale wear marks, now scheduled for ferry flight to Wright Field for operational evaluation tests. The perfect test bed. On a moonless night in late October, long after the last shift had clocked out and the hangars had fallen mostly silent, Farah, Jenkins, and Rodriguez moved like shadows. The only sounds were the distant drone of a late-night transport, the metallic echoes of their tools, and the frantic pounding of their own hearts. They worked quickly, efficiently, illuminated by the focused beams of their lanterns. Farah guided their hands, pointing out the 6 critical points he had identified. Jenkins, with his precise touch, cut the lengths of safety wire. Rodriguez, strong and steady, secured them, twisting the ends with specialized pliers until the tensioners were perfectly set, almost invisible against the maze of cables. No forms were filled out. No supervisors were informed. They were technically sabotaging military equipment, an offense punishable by court-martial. But in Farah's mind, they were doing precisely the opposite. They were saving it. They were giving this Mustang, and by extension, the men who would fly it, a fighting chance. As the last tensioner was secured, Farah looked at the gleaming P-51, its silver skin reflecting the dim light, and felt a surge of defiant hope. The secret, 18-cent fix, was now part of its very being. The next morning, P-51B 43-112434 would fly to Ohio, carrying not just a pilot, but a silent, unauthorized experiment that could change the course of the air war. The modified P-51B, serial number 43-112434, departed Inglewood under the pale light of dawn, a silent, unauthorized experiment soaring towards Ohio. Its pilot, unaware of the clandestine work performed inside its airframe, settled into the long ferry flight. 2 weeks later, back in the North American Aviation hangars, Sergeant John Farah's anxiety was a constant, low thrum beneath the din of the factory. Had the plane arrived safely? Had the modification worked? Or had his audacious gamble resulted in disaster, sealing his fate as a court-martialed saboteur? The answer arrived not as a punitive summons, but as a cryptic phone call. It was late November when Farah was pulled aside, his heart pounding. The call was from right field. On the other end was Captain Technical Officer Richard Hayes, 29, an aeronautical engineer from MIT, now a flight test officer. His voice was precise, edged with an engineer's curiosity. "Sergeant Farah," Hayes began, "we have an aircraft here, 43-12434. Our test pilots have noted exceptionally good control characteristics at altitude, significantly better than other P-51Bs from the same production block. Our inspection team found some unauthorized modifications. Are you responsible for these wire tensioners?" Farah's breath hitched. Relief, profound and dizzying, washed over him, quickly followed by a surge of defiant pride. "Yes, sir," he replied, his voice steadier than he felt. "I am." Hayes, initially skeptical of any unsanctioned tinkering, was an engineer first and foremost. The performance data was undeniable. Pilots, pushing the Mustang through simulated combat maneuvers at 20, 00, 25, 00s, even 30, 00 feet, reported a surprising responsiveness, a lightness of controls previously unseen in the P-51B. The unauthorized wire tensioners, discreetly installed, had gone unnoticed until the superior handling prompted a forensic examination of the aircraft's control systems. Hayes, despite the flagrant breach of protocol, recognized a potential breakthrough. He couldn't ignore the empirical evidence of dramatically improved performance. Reluctantly, yet compelled by the data, Hayes authorized a series of field tests. 10 more P-51Bs, fresh off the assembly line at Inglewood, were earmarked for Farah's modification. This time, the work was done under the quiet supervision of Hayes's team, ensuring consistency, though still officially unapproved. The results were unequivocal. Throughout November and December 1943, the modified aircraft consistently demonstrated control forces 30-35% lighter at altitudes above 20, 0 feet during aggressive combat maneuvers. There was no measurable degradation in structural integrity or reliability. More critically, test pilots reported a newfound confidence in executing demanding maneuvers at high altitude, a psychological factor impossible to quantify on paper, but invaluable in the chaos of real combat. Word of the Farah fix, though officially unacknowledged, began to spread like wildfire through an informal, clandestine network. Mechanics, always eager for a better way to do things, swapped diagrams and tips. Pilots, hungry for any edge, spoke in hushed tones of that one Mustang that really handled. Officers like Major James Howard, 30, a former Flying Tiger and Medal of Honor recipient with an engineering background from Pomona College, became quiet advocates. Howard, commanding the 356th Fighter Group, understood intimately that a pilot's trust in his aircraft's responsiveness was paramount. He began making discreet inquiries, pushing for enhanced maintenance checks that subtly included Farrer's modification on his unit's P-51s. This underground dissemination allowed the modification to bypass the months, if not years, of bureaucratic red tape that would have otherwise stifled its adoption. By January 1944, a trickle of P-51s, many of them clandestinely modified, began arriving in England, destined for the 8th Air Force. The air war over Germany was intensifying, the stakes growing higher with every bomber mission. The 354th Fighter Group, one of the first units to operate the Merlin-powered Mustangs over Europe, had approximately 40% of its aircraft equipped with Farrer's tensioners by February. These were the early days of deep escort missions, pushing far beyond the previous range of Allied fighters into the heart of the Reich. Among these pilots was Lieutenant Glenn Eagleston, 22, from Farmingdale, Long Island. Eagleston was a technically precise pilot. His mechanical engineering studies at university cut short by the war. On February 20th, 1944, he found himself high above Leipzig, Germany, on an escort mission targeting vital German aircraft factories. The sky was a vast, cold expanse, broken only by the contrails of the B-17s he protected, and suddenly, the menacing silhouettes of two Messerschmitt Bf-109G-66. They emerged from the sun, intent on breaking the bomber formation. The Germans initiated a classic Luftwaffe tactic, a bracket attack. Two 109s, one high, one low, converging from opposite directions, designed to overwhelm the target fighter, forcing it to choose one threat and exposing it to the other. It was a maneuver that had claimed countless Allied aircraft, relying on the superior high-altitude maneuverability of the Messerschmitts. Eagleston, flying P-51B A5, one of the discreetly modified Mustangs, found himself in their deadly crosshairs. He saw the first 109 closing fast, its machine guns spitting fire. Instinct took over, but his Mustang responded with an immediacy that surprised even him. Eagleston executed a high G barrel roll, combined with an abrupt, coordinated yaw, a maneuver his instructors would have deemed impossible in a P-51 at 26,000 feet. The controls, usually heavy and resistant at this altitude, felt light, almost eager. The Mustang literally spun around its own axis, while simultaneously changing direction, demanding extremely rapid and precise aileron inputs. The first 109, unable to track such an agile target, overshot completely, streaking past Eagleston's wingtip by less than 50 feet. The second Messerschmitt attempted to follow, but its controls, afflicted by the very high-altitude hardening that had plagued the unmodified Mustangs, lagged. It couldn't match Eagleston's violent reversal. In a blur of motion, Eagleston reversed his own trajectory, his Mustang snapping into position. He was now 200 yards behind the German leader, a perfect shot. His thumbs found the firing button. A searing stream of 50 caliber tracers tore into the 109. Two explosions in quick succession blossomed on the German fighter's fuselage, followed by a shower of debris as it spiraled out of control towards the frozen landscape below. The second 109, its pilot momentarily stunned by the impossible maneuver, broke off its attack, diving for the clouds. Eagleston, his heart still thundering, scanned the sky. Both threats neutralized. He rejoined his formation, adrenaline coursing through him. In his after-action report, filed hours later, Lieutenant Eagleston made a specific, if understated, note. Controls responded exceptionally well at critical altitude. He attributed it to a good airframe, perhaps a well-maintained example. He had no idea that his victory, his life, and the lives of the bomber crew he had just protected were owed to an 18-cent piece of wire installed by a mechanic from Detroit he would never meet. The unofficial fix had just claimed its first two victories, marking a silent, pivotal turning point in the air war. While American Mustangs, now subtly enhanced, began to turn the tide of air combat, a growing unease permeated the ranks of the Luftwaffe. Over the frozen fields and industrial heartland of Germany, something unsettling was happening. Intelligence reports, filtering up through the command structure, began to document a disturbing shift. American P-51s were demonstrating a newfound aggression and agility at high altitudes, capabilities previously thought beyond their reach. Veteran pilots of the Jagdgeschwader, men hardened by years of desperate combat, reported encounters that defied their understanding of enemy aircraft. These weren't isolated incidents. In March 1944, Hauptmann Klaus Weber, 26, an experienced pilot from Jagdgeschwader 3 with 47 confirmed victories, was shot down over Brunswick. During his interrogation, conducted by a cold, meticulous intelligence officer, Weber recounted a harrowing dogfight against a P-51. "The American pilot," he stated, his voice still edged with disbelief, "executed a series of high-speed reversals at approximately 8,000 meters, maneuvers I considered impossible for the type. It was unnatural." His words, transcribed and analyzed, added to a growing dossier of anecdotal yet consistent evidence. This information reached the highest echelons of the Luftwaffe. General der Jagdflieger Adolf Galland, 32, a legend of German aviation with 104 victories and commander of the entire fighter force, read these reports with growing alarm. His sharp, tactical mind struggled to reconcile the accounts with known P-51 performance specifications. The American Mustang, while fast, had always been predictable in its high-altitude handling. Now it seemed a ghost in the machine was making it dance with the agility of a Bf-109, if not superior. The Luftwaffe High Command, already grappling with dwindling fuel supplies, inexperienced pilots, and overwhelming Allied numbers, theorized that the Americans had introduced a new variant of the P-51, perhaps equipped with sophisticated servo tabs or a hydraulic power assist system. Orders were swiftly issued, prioritizing the capture of an intact new model Mustang for examination. The technical intelligence officers believed such an aircraft would reveal vital design secrets. The opportunity came in April 1944. Lieutenant Robert York, 24, a pilot from the 307th Fighter Group, found himself in a desperate situation over occupied Belgium. His P-51B, severely damaged in combat, was losing power. With a grim resolve, York skillfully brought the crippled fighter down in a forced landing deep behind enemy lines. Before German troops could reach him, he managed to set fire to the cockpit and instrument panel, destroying crucial intelligence. He was captured, becoming a prisoner of war. However, the central fuselage section, though scorched, remained relatively intact. News of the downed Mustang reached Messerschmitt AG in Augsburg with urgent speed. A team of engineers, led by the distinguished chief engineer Heinrich Müller, 41, a veteran of Bf-109 development since its pre-war variants, was dispatched to the crash site. They arrived with high expectations, believing they were about to uncover a significant technological advancement. Müller, a man of precise calculations and rigorous design principles, meticulously examined the wreckage. His team, equipped with specialized tools, painstakingly dismantled the surviving sections, focusing intensely on the flight control systems. Days of careful inspection turned into a week. They found no elaborate hydraulic system, no revolutionary servo tabs, no fundamental innovations in design. The structural integrity was consistent with standard P-51B schematics. Yet, the pilot reports persisted. What was the secret? Müller, a man accustomed to finding complex engineering solutions, felt a growing sense of frustration. Then, one of his junior engineers, inspecting a damaged section of the aileron cable run, pointed out something almost invisible. Small, almost primitive loops of stainless steel wire, carefully secured at specific points along the cable guides. They were simple, almost crude, seemingly insignificant. Müller himself examined them, tracing the path of the cables, seeing how these seemingly trivial wires subtly held the main cables in a more precise alignment. The elegance of the hack was breathtaking in its simplicity. The German technical reports compiled after their investigation described the modification with a mixture of professional respect and palpable consternation. Primitive, aber wirksam. Primitive, but effective. The engineers were simultaneously relieved that there was no advanced enemy technology they had overlooked, and profoundly embarrassed by the sheer simplicity of the solution. It was so basic, so low cost, so obvious, in retrospect, that it stung. More problematic for the Luftwaffe, it was a solution that couldn't be easily replicated in their own aircraft. German fighters, like the Bf-109, utilized fundamentally different control systems, often employing push-pull rods instead of cables in many areas. Ferrous wire tensioners were a specific tailored fix for the P-51's cable-based architecture. This trivial modification had been deployed by the Americans while the Luftwaffe still struggled with bureaucratic delays in approving even fundamental improvements to their own armament and propulsion systems. It highlighted a flexibility and adaptability in the Allied system that Germany, with its rigid hierarchy, seemed to lack. Back in the United States, the empirical evidence from Wright Field and the growing anecdotal reports from the combat theater could no longer be ignored by the Army Air Forces. In May 1944, months after Ferrous' clandestine installation, the modification was finally formalized. It was officially designated Field Modification 184. A technical order, TU, was issued, authorizing its installation on all P-51B, C/D, and K variants in service. The TO was remarkably simple: 6 clear diagrams illustrating the precise installation points, specifications for the material, Type 302 stainless steel safety wire, 0.41 inches in diameter, and basic instructions. Installation time, 30-45 minutes per aircraft. Cost, $0. 18 in materials. No specialized tools were required. Field mechanics, empowered by this official decree, could now implement the modification using resources already available at any base. A swift, decentralized deployment that would soon sweep across the 8th and 9th Air Forces. The mad mechanics' forbidden fix had gone legitimate, just in time for the intense air battles of the coming summer, with the official designation of Field Modification 184 in May 1944. What had been a mechanic's defiant gamble became standard procedure. The simple technical order, so stripped of bureaucratic jargon, was a testament to the urgency and undeniable effectiveness of the fix. It spread like wildfire through the maintenance echelons of the USAF. Mechanics in dusty field depots and bustling rear echelon hangars alike, empowered by the official directive, swiftly implemented the change. By August 1944, a mere 3 months after its official adoption, over 200 operational P-51 Mustangs had received the 18-cent modification. It was a rapid, decentralized deployment, a quiet revolution happening in the shadows of the larger war. The impact was not long in coming, etched into the stark, unforgiving statistics of air combat. Between June and December 1944, the period of the most intense aerial warfare over Germany, the numbers told a brutal and undeniable story. P-51s equipped with Field Modification 184 achieved an aggregate victory ratio of 4.81 against German fighters in engagements above 20,000 feet. This compared dramatically to a 3:1 ratio for unmodified Mustangs, still operating in some secondary theaters or early batches. The difference of 1.61 might seem a dry academic figure on paper, but in the unforgiving crucible of the European skies, it translated into hundreds of American pilots who returned to base. Their lives saved, instead of becoming flaming wreckage plummeting towards enemy territory. In specific, close-quarters combat against the Luftwaffe's best, the agile Bf-109G-10 and the formidable Focke-Wulf FW-190D9, the advantage conferred by the subtle modification was even more pronounced. American pilots entered every engagement with absolute confidence that their aircraft would respond precisely and instantly, even at the thin, frigid altitudes where dogfights were decided. On the German side, the impact was devastating. In September 1944, General der Jagdflieger Adolf Galland, his face etched with the strain of a losing war, penned a grim and foreboding report to Reichsmarschall Hermann Göring. The situation for the German air defense was critical, plagued by a multitude of crises: chronic fuel shortages, grounding squadrons, the crushing numerical superiority of the Allies, and the desperate, hurried training of inexperienced pilots. But among these myriad woes, Galland singled out a specific qualitative shift in the enemy. The American Mustangs now demonstrate superior maneuverability at all combat altitudes. Our pilots can no longer rely on handling advantages at high altitude. It was a complete, bitter reversal of fortunes from just a year prior, when German fighters had reigned supreme above 20,000 feet. The strategic landscape of the air war had shifted irrevocably, in significant part due to a piece of wire installed by mechanics who had never set foot on German soil. The psychological blow to the German fighter arm was profound, undermining the confidence of their dwindling pool of veteran pilots. Yet, Sergeant John Ferrer, the unassuming mechanic from Detroit, whose ingenuity had quietly turned the tide, never received public recognition for his groundbreaking innovation during the war. His promotion to technical sergeant in July 1944, a routine advancement, bore no official connection to the modification. He remained at North American Aviation's Inglewood plant, working the production lines, ensuring every Mustang sent to war was as perfect as he could make it. He served out his enlistment, a diligent, anonymous cog in the vast war machine. When the war finally ended in November 1945, Ferrer returned to his hometown of Detroit. He resumed a quiet, civilian life, working as a maintenance supervisor for the Ford Motor Company, overseeing the assembly lines that now churned out cars instead of tanks and aircraft components. He retired in 1980, a modest man who had made a profound difference without fanfare or medals. It was not until a rare, recorded interview in 1977 for an oral history project by the Air Force Historical Foundation that Ferrer briefly revisited his wartime contribution. His voice, older but still carrying the same unassuming earnestness, described his invention with characteristic humility. "It wasn't rocket science," he mused, a faint smile on his lips. "It was just listening to what the pilots were saying, watching what the airplane was doing, and trying to fix the problem with what you had at hand. In wartime, sometimes you can't wait for a committee to approve everything. Sometimes you just have to do what needs to be done and hope it works. I was lucky it worked." His quiet words, unassuming and devoid of ego, belied the immense impact of his luck. The story of field modification 184, Ferrer's 18-cent fix, later became legendary within Air Force technical schools. It was studied, not for its complex engineering, but as a perfect example of practical innovation at the operational level. It symbolized something fundamental about how technological wars are truly won. Not solely through superior designs conceived on engineers' drawing boards, but through the crucial ability to identify real-world problems in the field and implement rapid, effective solutions, even when those solutions circumvent established bureaucratic protocols. The proper engineering solution, a redesign involving new hydraulic systems or complex servo tabs, would have cost millions of dollars and incurred months, possibly years, of crippling delays. Ferrer's solution, costing just 18 cents in materials, was implemented in weeks. In that brutal wartime calculation of time, cost, and effectiveness, the American simplicity utterly defeated German bureaucratic complexity and theoretical engineering purism. It was an admission that went beyond mere technology. It spoke to organizational culture and the agility to adapt rapidly at the operational level. In April 1945, as the final, desperate battles raged, P-51 Mustangs, almost all now fitted with Ferrer's silent legacy, escorted B-17s and B-24s deep into the heart of a crumbling Germany. They met increasingly weaker resistance, German fighter formations decimated, their pilots outmatched. Few American pilots, roaring confidently through the shattered skies, knew about the 18-cent piece of wire that helped keep them alive, that allowed their aircraft to snap into turns and rolls with a responsiveness that baffled their desperate enemies. They simply knew their Mustangs handled beautifully, that they could trust their controls when faced with the last, furious lunges of the Luftwaffe. On the other side, surviving German pilots faced adversaries who seemed to improve constantly, even as their own resources dwindled to nothing. It wasn't just numbers or training. It was the accumulation of 1,000 small advantages, each seemingly trivial, but collectively decisive. And one of the most crucial of those 1,000 advantages had been forged by a mechanic from Detroit, who refused to accept that thousands of dollars worth of aircraft should suffer from a solvable flaw, and had the audacity to fix it with the most basic materials at hand. His was a silent legacy, a testament to the unsung heroes who win wars, one ingenious, unauthorized fix at a time. In the grand symphony of war, where the thunderous roar of Merlin engines and the desperate ballet of dogfights decided fates, a nearly invisible thread, costing mere cents, wove itself into the fabric of victory. The scream of the P-51 Mustang, once tempered by unresponsive controls at crucial altitudes, now sang a song of lethal agility. High above the crumbling Reich, American pilots, imbued with audacious confidence, danced through skies once dominated by the enemy, unaware of the 18-cent secret hidden deep within their aircraft's structure. This silent revolution, born of one mechanic's defiance and intuition, reshaped the very nature of aerial combat, turning the tide with ingenuity rather than brute force or complex factory-fresh designs. John Ferrer's legacy isn't carved into bronze monuments or emblazoned on victory banners. It's etched into the countless untold stories of pilots who returned home, their lives saved by a fraction of a second, by a control input that felt just right. It's remembered in the frustrated admissions of German engineers, baffled by the elegant simplicity that defied their own bureaucratic complexities. It is a profound testament to the truth that wars, and perhaps even the greatest challenges of humanity, are not always won by the loudest pronouncements or the most sophisticated technology. Often, victory belongs to the quiet innovators, the hands-on problem solvers who see beyond the blueprints, who dare to defy convention, and who, with humble materials, mend the unseen flaws of a flawed world. It reminds us that true genius can often wear a mechanic's uniform, and profound heroism can be woven from 18 cents of wire. This story makes us wonder, how many other critical turning points in history were shaped by such anonymous acts of courage and brilliance? How many unsung heroes, battling bureaucracy and doubt, truly changed the course of events? Share your thoughts below. Who do you believe are history's most overlooked innovators? Don't forget to like this video if you found this untold chapter of history compelling, and subscribe to WW2 Secret Files for more stories from the shadows of the greatest conflict humanity has ever known. Until next time, keep exploring the past.